Most of them are making up the quiz from yesterday. So they'll catch up on these notes later at some point. All right, so we're going to do kind of two different things today. We'll see how far we get. But the first thing we're going to do is talk about two additional derivative shortcuts to add to our list. And then the second thing is I'm going to show you kind of how to figure out derivative values on the calculator, because half of the AP test you can utilize a calculator, so I want to make sure that we're good with pressing the right buttons, using it the appropriate way, all that jazz. So first off with the shortcuts. We're going to take a look at two new ones today. I think you're going to like them. They're pretty simple. We just got to get used to them. But they're not as involved as the product rule, quotient rule, chain rule. They're more of like quick shortcuts. Like, you know how the derivative of sine is cosine? Like, that's pretty quick. It's not like a process like the product rule, chain rule, and quotient rule are. So these are going to be fairly new, or fairly quick rather. So on page 171, we're going to take a look at exponential functions, specifically e to a power. We've all seen e before, right? 2.718. Okay, so we're going to take a look at how we can figure out the derivative of those. Now, I know in previous shortcuts I've used the limit definition, and we eventually developed the shortcut. But using the long limit definition of a derivative for these is a little tedious, and it involves some mathematical concepts that we haven't really discussed yet. So for these two shortcuts, I'm just going to give them to you, and then we're going to practice them. Okay, it's not really my, not really the method I prefer to use, because I want you to understand where the shortcut comes from, but we can't do that just yet. So is that okay with you if I just give you the shortcut and we use it? I don't think there's going to be any objection, or at least I hope not. Okay?
No, that's good.
Okay, so let's say we have an original function that looks like e to a power. Now that power normally has a variable with it, and that power could be 2x plus 1, it could be a trig function, it could be a square root, who knows, okay, but we have e to some type of power. If that's the original function, then this is what the derivative looks like. I'm going to write it down, and I want you to think about what it says or what it represents. That's it. Yep.
What's E again?
E is, you know how pi is like 3.14? E is 2.718 with more decimals. It's a special irrational number.
Where does it come from? Pi? From the circle?
Pi comes from the circle, right. So there was a mathematician named Euler. I think he was Swiss. He's the one that kind of discovered that number. So that's why we call it E after his last name.
What is his last name?
Euler, E-U-L-E-R. That's how it's spelled. Yeah. It kind of does, right? Because doesn't the chain rule end with like multiplying by a derivative, like of the inside stuff? Okay, it kind of looks like a chain. So take a look at this. If your original function is e to some power, notice how that shows up in the derivative, right? So you're just basically copying down the original problem, but you have to multiply by the derivative of the power. Okay, whatever that stuff is up there. Okay, so let's check out our first one. Notice how the original function is e to the power of sine. So if we wanted to figure out the derivative, we simply keep the original function the same, but then we have to multiply by the derivative of the power. So what's the derivative of sine?
Cosine.
Cosine. Good. And we're done. You found your first exponential derivative. Hooray, right? Now that's a simple one. We're going to get a little bit more involved, but that's the basic premise. Okay? So for the derivative of e to a power, you simply keep the original stuff, e to that power, times the derivative of that power. Let's try the next one. We have e to the 2x plus 3. So for the derivative, we would keep the original exponential function times the derivative of the power, 2, okay? So you can leave it like that, but just like with all the other derivatives we've done, you can rearrange it or clean it up. So this 2 you could move out front as a coefficient, because normally those numbers are written first, not last. All right, so there's your other derivative. Not too bad of a shortcut, right? Let's try the next one. Okay. This time we have a coefficient out front, that number 3. How have those coefficients kind of worked with other derivatives we've done? For instance, if I were to write down 3 sine of x, what would you say the derivative was? 3 cosine. So whenever you just have a number out front, okay, a coefficient, it stays there for the derivative. You just keep it. So we really just have to figure out the derivative of e to the 2x. So the derivative of e to a power is simply e to the power, but you got to multiply by the derivative of that power, which would be 2. So if we kind of clean that up, we can do 3 times 2, which would give us a new coefficient of 6. Do we get the basic idea? Okay, let's try to amp it up a bit. Okay, look at the next one. How might you want to tackle that derivative? Yeah.
Does it work?
Never mind, okay. What do you think, Liam?
Are we gonna have to use chain rule at all, or can we just do the natural?
So we do have that. We do have the exponential showing up. If you were to read this out loud, it's not necessarily chain, because I know you see like inside, outside, but if you were to read it out loud, this would be 2x plus 3 times. Okay, so that's indicative of a product rule, right? Not necessarily chain. So we're going to have to do the product rule. That's kind of the main one. But in that process, notice how we're going to have to use the exponential shortcut. Okay, so let's go ahead and use our product rule. Our first function is 2x plus 3. And then we have to write down d2. So we have to figure out the derivative of that exponential, which would just be e to the 3x times 3. All right, so that's 1d2, and we now have to add 2, and then d1. So the derivative of 2x plus 3, we got just 2. All right. So a lot of parentheses in there. Let's go ahead and clean it up, maybe distribute some things in. If we were to distribute in an e to the 3x, but also a 3, okay, let's see, 2 times 3 would give us a 6, and then distributing in the exponential would leave us with an e to the 3x power. If we did the second distribution, we'd have a 3 times 3, which is a 9. And then distributing in the exponential, we have an e to the 3x. And for the last term, maybe we can just write the 2 out front as the coefficient. So with all the parentheses gone, maybe we can combine some like terms. Looks like we have a 9 e to the 3x and a 2 e to the 3x. So we can rewrite those as 11 e to the 3x. We can't combine the other one because that one has an extra x in it. Okay. Are we doing okay? Mm-hmm. Okay. Let me ask you this. Okay, so this is one way you can represent the derivative, but we can perhaps write it a different way. Can we try to maybe factor this? Is there a GCF that we can pull out? Is there something that both of these have in common that we can remove? Yeah.
E to the 3x.
An e to the 3x. Okay, so we're left with a 6x plus 11. I'm not saying you have to do that. I'm just saying in the probably foreseeable future, it would be useful for us to do that. So if you can pull out a GCF, I might recommend you doing that. Okay, let's try the next one. Okay, think about your shortcuts. What do you want to try? If you were to read it out loud, maybe that might help you to determine which one to use. Yeah? Product. Yep, we got x squared times e to the 2x. So let's go through product. We have 1. And then d2, we need the derivative of that exponential. So that'd be e to the 2x times 2. Let's finish the product rule. We have 2 times d1. So let's see. All the terms or all the pieces in the first term are being multiplied together. You can rearrange them however you want. Normally numbers are written first, then variables, then maybe lastly the exponential, but order doesn't really matter when you multiply, so however you want to write it is fine. And then the same thing for the last term, maybe we can move the 2x out front. Okay, so you could leave that as the derivative. Maybe you can factor it. I'm not saying you have to, but maybe it's a good practice. Is there a GCF you can remove? Something they all have in common? Yeah.
E to the 2x.
Okay, an e to the 2x, definitely.
Oh,
A 2. Yeah? A single x, yep. Okay, so if we remove that from the first term, we're left with a single x. And since we're removing all of that from the last term, we're just left with a placeholder of 1. That way, if we were to distribute the GCF back in, it would still be there as a term. All right, so there's that derivative. Not too bad. All right, let's try the last one. I'm hoping we're getting in the habit. Whenever you see a root, go ahead and rewrite it as a power. So where do you guys want to go from there? Yeah, we got a chain. Do you see inside, outside? All right, so let's go ahead and do our chain. We're going to bring down the outer layer of a half, keep the inner layer. Make sure you write down the new power. And then to finish off the chain, if we remove the outer layer, now we have to remove the inner layer, aka multiply by its derivative. So the derivative of e to the 2x minus 6 is e to the 2x minus 6, but then times 2. Okay, the derivative of that power. So since we use the chain rule, everything's being multiplied together. It's either going to move to the top or the bottom of a fraction. Let's see, we have a 1/2, so we can put the 2 down below. The quantity that we have is being raised to a negative power. Yeah?
Wouldn't the 2 and the 1/2 cancel?
Maybe you see that initially. Okay, so if you want to see that initially, that's fine. Some people wait till the end to cancel those out, but that's okay. So maybe we'll do that. Okay, so we're left with e to the 2x minus 6. Do you see something? Yeah?
E within the parentheses
Yep.
is the brought up to the negative 1/2 power, so we can bring it to the bottom.
Yep.
The square root.
Okay, so we'll bring it to the bottom, and you can rewrite it as a square root if you want to, or leave it as 1/2, doesn't matter, they mean the same thing. This e to the x, though, stay up top. Yep, it does not have a negative power. Okay, now rewriting it as a square root is possible, but I didn't want to do that for particularly for this one, because notice how this e is raised to a positive power, and if these bases are the same, what do you do to powers when you divide? You subtract the powers. So 1 minus a half is a half, right? So now that you kind of got rid of that fraction, you could rewrite it as a root if you wanted to. All right, so there's your derivative. You notice anything special about that?
It's the original equation.
It's the original equation, yep.
That's so stupid.
Interesting. Oh, come on.
Oh, we still have working on it.
I know. That happens.
That entire thing is
We did all of it.
equation.
Oh, wait. Well, hold on. I'm going to burst your bubble even more, okay? We could have done this a lot simpler. You ready? Uh-oh, right?
That's what I'm excited.
Okay, so notice how chain rule works out in the end. The derivative actually is the same as the original. Kind of interesting tidbit. Let's take a look here, okay? When we rewrote it, okay, as a power of a half, if you have a power to a power, how can you combine those? Before we even take the derivative, can we continue to simplify? If you have a power to a power, how do you combine them together? Multiply, okay? So this would be, if we multiplied in the 1/2, this would be e to the x minus 3, right? Could we take the derivative from there? The derivative of e to the x minus 3 is e to the x minus 3 times 1, which is just itself, right? Take a look here. Isn't this what we got for the derivative? If you were to distribute in the 1/2, wouldn't you get e to the x minus 3? Same thing. Okay, so maybe the chain rule wasn't necessary, okay, but you guys are getting really good at these shortcuts that it's going to work out either way. Remember how in some of the other sections we've been talking about, like, moral of the story, simplify if possible first before you take a derivative? Okay, same thing kind of going on here, but since these are exponential functions, you're going to have to use properties of exponents. So if you can simplify it, it can make the derivative a little bit easier. I'm not necessarily saying this is difficult, okay, because we're getting good at the chain rule. I'm just saying that it might be a little bit more work. All right, so if you can simplify, go for it before you take the derivative. All right, let's go ahead and check out the back. Forgot to erase from last class. Okay, so at the top, taking a look at it, derivative shortcut, what do you kind of see? Quotient rule. All right, so we have low times d high, bless you. Notice how the top function is the exponential e, so we need, the derivative would be e to the 5x times 5. All right, so low d high minus high times d low, square the bottom, and away we go. All right, so there's the initial derivative, but we're going to clean it up, simplify it a little bit, make it look nicer. So our first term, everything being multiplied together, we could do 3 times 5, which is 15. And then the x squared e to the 5x. The next term, if you want to reorder them, you can. And since we have just one term in the denominator, maybe we can square it. Okay, that's easier than having two terms and having to go through a FOIL process. So if we did 3x squared squared, that would be 9x to the 4th. All right, let's see if we can keep going. If you take a look at the numerator, is there a GCF we could pull out? A factor? Yeah. And e to the 5x. Anything else they have in common? A 3. Factor of 3. Anything else? Yeah? A single x. Notice how this one has x squared, this one has x. So they both have one x in common. So if we removed that, we'd be left with a 5x minus 2. So by factoring, maybe we can actually cancel some things out because we're working with division. Notice how the 3 divided by 9 could simplify. The x divided by x to the 4th could simplify. So let's see, in the end, we would have e to the 5x up top with a 5x minus 2, and then a 3x cubed down below. Are we doing okay with the exponential shortcuts? Pretty straightforward? Okay, simple shortcut. All right, let's check out logs. Okay, so the natural exponential function is the e. We know natural logs look like ln. So let's say we had an original function, which was the natural log of something. Okay, something's on the inside of it. It could be 2x plus 1, it could be sine, it could be a square root, who knows, but something's on the inside of that natural log. All right, so here's the shortcut for this one. If this is your original function, then the derivative looks like this. Can you think about what this notation is telling you? What does the derivative of a natural log kind of look like? Can you describe it? What do you think, Liam?
It's a fraction.
It's a fraction. Okay, so it's definitely a fraction, and there's no more natural log there. Okay. What's going on with the f prime and the f? You want to keep going? Yeah.
The numerator is the derivative of x.
Okay, so in the fraction, the numerator is the derivative of the inside of the natural log, whereas the denominator is simply just the inside of the natural log. So the natural log doesn't really mean anything in terms of the derivative. Okay, this is just kind of a clue to us that this is what the derivative should look like. Okay, but it's mostly all about what's inside the natural log that we're concerned with here. So let's go ahead and check out the first one. Okay, so we have the natural log of 2x minus 3. So the fact that we have a natural log means that derivative is going to be a fraction. The numerator is the derivative of the inside, whereas the denominator is simply whatever the inside is. So what might this derivative look like for that natural log? Good, Ryan?
The derivative
Mm-hmm.
of the function inside is 2.
Okay, so that's our numerator. Good.
And the original function is 1, 2x minus 3.
Yep, the original inside is going to be on the bottom. Perfect. So that's the derivative for this natural log function. Pretty simple shortcut. I think these kind of go hand in hand. They're pretty quick for us to kind of grasp. Let's go ahead and try the next one. Okay, so the derivative of the natural log is going to be a fraction. We need the derivative of the inside of the natural log to be up top, whereas just the original inside is in the denominator. Okay. Sometimes you might be able to simplify these a little bit further, like factoring and canceling things out, but it doesn't look like anything's going to happen in this case, because if we tried to factor it, we could only pull out a 2 from the top and an x from the bottom. But notice how none of those kind of match or cancel out from there. So we're just left with that as the final derivative. We doing okay? All right, let's try another one. We're going to figure out the derivative of a natural log. So boom fraction. What's the derivative of the inside of that natural log? Negative sign. Good. The inside quantity of the natural log is cosine, so you could leave that as your derivative. But since we're working with trig, maybe we could simplify it. Negative sign over cosine, yeah.
Negative tangent.
Negative tangent. Good. All right, let's check out the next one. This one is written a little differently. Do you notice how the 3 examples we've done have had parentheses around them? Like it's the natural log of something. This one doesn't have the parentheses there, but you could write them in if you wanted to. Okay, very similarly, sometimes, like when we write trig functions, for instance, cosine of 3x, there technically should be parentheses around the 3x, just sometimes we don't write them. So the same thing kind of holds true for logs. Hopefully we get in the habit of every time we see a root, we rewrite it. All right, so let's go ahead and tackle the derivative. The derivative of a natural log is a fraction. We need the derivative of the inside over the inside. How do you guys want to find the derivative of the inside? Yeah? We got a chain, yep. We got inside, outside. Okay, so chain rule, we'll find the derivative of the outer layer, so we'll bring down the 1/2, keep the inside, don't forget your new power, times the derivative of the inner layer, which is 2. All right, let's clean it up. Yeah?
2 and the 1/2 cancel.
Good.
And you subtract the exponents.
Okay.
And you end up with -1.
Okay, so negative 1/2, notice how the bases are the same. So negative 1/2 minus 1/2 would be -1. That's signifying that the base is in the denominator with a positive 1 power. The negative just means it's in the bottom. Okay, so notice how if you have something to the first, you don't necessarily have to write it like that. So you could just say 1 over 2x minus 4. Good. How are we doing with the shortcuts? Pretty good? Just fine. Peachy. All right. Bell's been ringing a little bit. We unfortunately didn't get to the calculator stuff, but we'll do that tomorrow. Okay? So just remember to come in tomorrow with a calculator and grab one.